This is Professor Rogers. In this presentation, we discuss the normal distribution. In this presentation, we describe the characteristics of the normal curve, show how to convert any distribution of points to the standard normal distribution, summarize simple tests for normality, and demonstrate how to transform a non-normal distribution of data into a normal distribution. We all know the normal distribution. It is commonly called the bell curve. All normal curves are a variation of the standard normal curve, which has a mean of 0 and a standard deviation of 1. This curve is often abbreviated using the capital letter N with a 0 followed by a 1 in parentheses, 0 for the mean and 1 for the standard deviation. The normal distribution is one of several distributions encountered in statistics, but arguably the most important to understand. Many inferential statistics assume numeric data is normally distributed. I stress that what we are discussing applies only to numeric data. We will deal with categorical data elsewhere. Characteristics of the normal curve provide the basis for understanding confidence intervals and statistical significance. When we need an example in this presentation, it will come from a data set containing the 50 states and the District of Columbia, a total of 51 observations. We will look at three variables: the number of people, population for short, the poverty rate, calculated as the percent of people living below the poverty line, and percent urban, the percentage of people living in census-defined urban places. The normal distribution has three characteristics. First, the mean, median, and mode are the same points. Second, the distribution is symmetrical. If one side of the curve were folded on top of the other side of the curve, the shape of the left half of the curve would be the same as the right half. Finally, the distribution of points under the curve is known, and is expressed geometrically as the area under the curve. The mean and the standard deviation tell us a lot about the curve. About 68% of points fall within one standard deviation of the mean. About 95% of points fall within two standard deviations of the mean. Over 99% of points fall within three standard deviations of the mean. Thus, if we assume that a distribution of points is normally distributed, the combination of the mean and standard deviation give us enough information to make a sketch of the distribution. Any distribution of points can be expressed in units of the standard normal distribution by converting its values to what is called a z-score or standardized score. The z-score standardizes any normal curve into the standard normal curve. The calculation is simple. Subtract the mean from any point and divide by the standard deviation. If the point is less than the mean, the z-score will have a negative coefficient. If the point is more than the mean, the z-score will have a positive coefficient. Here the poverty rate for Ohio is used as an example. The national mean for the poverty rate is 15.257, and the standard deviation is 3.3043. The value for Ohio is 16.4. These numbers are plugged into the equation and we determine the z-score with simple arithmetic. Thus we find that the z-score for Ohio is approximately 0.35. Whether the z-score is positive or negative depends on the relationship of the observation to the mean. Ohio has a poverty rate greater than the national mean, so its z-score is positive. Here is the calculation for Pennsylvania. Pennsylvania's poverty rate is less than the national mean, so its z-score is negative. With this information, the location of the values of these states can be pinpointed on the standard normal curve. Their approximate location is shown here. The mean of the distribution has a z-score of 0. The score of a 0.1 standard deviation above the mean is 1. The z-score of a 0.1 standard deviation below the mean is -1. All this information is useful, but we have yet to address a key question. Is the distribution of points normal? Many of the earliest statistics were developed to study natural phenomenon, which often conform to recognizable patterns and have only random deviations from the central tendency. Social behavior is very different, and we are continually concerned about whether our data conform to the assumption of normality. There are 4 easy ways to check for normality using histograms, statistics for skewness and kurtosis, and data on outliers in the explore command. The histogram provides a visual test for normality when we superimpose the shape of the curve on the graph using the normal curve option. Here are the 3 example variables. Notice that even though poverty rate and percent urban do not have normally looking histograms, the curves superimposed on these graphs look very normal. However, the curve superimposed on population is not normal. Thus, our visual test suggests that we could treat poverty rate and percent urban as normal, but we cannot treat population as normal. Skewness and kurtosis have statistical tests for normality generated by both the frequencies and explore commands in SPSS and PSPP. Here I show the statistics option from the frequencies command, which allows us to select skewness and kurtosis as measures of the distribution. Here are the statistics on the output. Skewness describes the wobble or lean of the distribution. The normal distribution is symmetric, but a distribution that is skewed is asymmetric, leaning one way or the other. We describe the lean using the location of the long tail. If the long tail is on the left side of the distribution is said to have a negative skew, or is said to be skewed to the left. If the long tail is on the right side of the distribution is said to have a positive skew, or is said to be skewed to the right. In our example, the population histogram has a right skew, or is skewed to the right. In the SPSS and PSPP output, the value of the skewness statistic is 0 if the distribution is normal. Recognizing that such a perfect distribution is rare, the issue is how much tolerance we should show for deviation from 0. Here's the rule of thumb. A distribution is seen as being too skewed to the left if the skewness number is less than -2, and it is seen as too skewed to the right if the number is greater than 2. Between -2 and 2, we do not regard the distribution as skewed. These numbers are highlighted in this output. Poverty rate and percent urban fall in an acceptable range. We do not regard them as skewed. Population has skewness greater than 2, so we regard population as skewed to the right. Kurtosis has to do with the height of the distribution. The issue is seen as important because it affects whether there is enough variation in the variable between the low and high values. After all, by definition, a variable has to have variation. If the distribution is flat, it is said to be platykurtic. Using the kurtosis statistic, we regard the distribution as flat if the kurtosis statistic is less than -2. We often do not care about this situation because a flat distribution has plenty of variation. We are more concerned about distributions that are too tall and too skinny, or what we call leptokurtic. We know this situation is present when the kurtosis statistic exceeds the value of 2. Here the kurtosis statistic is highlighted on the output. Note that again the only variable that is not normal is population. Another issue affecting the normality of a distribution is the presence of outliers. Outliers are points that are far away from the main distribution of points. Here I highlight the maximum value in the histogram for population in the state-level dataset. Notice that the point stands apart from the rest of the data. Outliers distort statistical summaries. They inflate or deflate the values for the mean and standard deviation, and they can affect the parameters of bivariate and multivariate analyses in ways that lead to erroneous findings. The question that we must address is whether the point is so far away from the main distribution that we care. To determine whether a point is an outlier, we use the explore command. The use of the explore command was discussed in this video series and the second video on descriptive statistics for numeric variables. Its path in SPSS and PSPP is Analyze, Descriptive Statistics, Explore. In the Statistics option box, we click on the Outliers box as well as the Descriptives and Percentiles boxes that we use with positional measures of central tendency and dispersion. The Outliers box gives us a table titled Extreme Values. This table gives us the 5 highest and 5 lowest values in the distribution. We use positional measures to determine whether a point is an outlier. With the low values of the distribution, a point is regarded as an outlier if we take the 25th percentile and subtract 1.5 times the interquartile range. On the high end of the distribution, we take 1.5 times the interquartile range and add to it the 75th percentile. Here are the calculations for outliers for the population variable worked out on each end of the distribution. On the low end, a point is an outlier if the population of the state is less than minus 6,282,594.5. The number is negative. Obviously, there are no states with negative population sizes, so we do not have to worry about outliers on the low end of the distribution. On the high end of the distribution, a state is an outlier if its population exceeds 14,697,617. When we look at the extreme values table, we see that 4 of the top 5 values are outliers. We can go to the data view and identify these states. By right-clicking on the variable name over the column, we get options to sort the data. Here I used sort descending, so the data file is now organized to go from the most populated state to the least populated state. I learned that the top 4 values in the distribution, the outliers, are California, Texas, New York, and Florida. For inferential statistics to work correctly, we need to fix distributions whenever they are not normal. The issue is complicated because the issues of skewness, kurtosis, and outliers might be related. If we address skewness, sometimes other issues go away. Here are a set of steps that I find useful. First, we do our checks for normality, which we have already done in this presentation. We look at the histograms and the statistics for skewness and kurtosis. It is possible that these different measures do not agree with each other, so we have to make a judgment call. I sometimes say that statistics is more like art than science, and this judgment call is one of the places where the artistic side of statistics appears. To fix skewness, we transform the data. On the left, we see the ladder of powers. There are 2 columns on the chart, the first column being the transformation we might perform, and the second one the corresponding SPSS code to be placed in the numeric expression. The value identity is the variable that we have untransformed. We move up the ladder if we have skewness to the left. We move down the ladder if we have skewness to the right. We use the compute variable command to make this transformation. The command is found under Transform in the top menus of SPSS and PSPP. The command box of the compute variable command is shown here. On the top left, we have the target variable box. We enter the name of the new variable we want to make there. Make sure not to use an existing variable name or it will be overwritten. The numeric expression is the equation for the transformation. This is the expression shown in the second column on the left. Whether we move up or down the ladder, we try one transformation at a time until we find one that works. We can go past the one shown here, but it is not customary because the extreme transformations are not intuitive. Notice some extra information added with transformations in the bottom rungs. The issue here is 0 and negative numbers. We cannot take a natural log for 0, so in cases like this we often shift the axis by adding a small number, like 0.5, to all observations. This number is called a start. Furthermore, we cannot take the log or square root of a negative number, so we would have to use even larger starts to shift the axis. Here is the histogram of population. Since the histogram is skewed to the right, we start down the ladder of powers with a logarithmic transformation. The new variable based on this log transformation is on the right. Notice how the curve looks much more normal now, and there are no points standing apart from the main distribution. Here are the descriptive statistics for population and its logged variable side by side. Notice how the logarithmic transformation brings the skewness and kurtosis within acceptable levels. The explore command should also be repeated to confirm the effect on outliers. Below the table is the calculation of the outlier breakpoint for the natural log of population. Any value over 17.9268 is an outlier by definition. Notice that none of the top values of the log variable exceed the threshold. We lucked out. Our first transformation was successful. If it were not initially successful, we would move one rung at a time until we were done. The thing about transformations is that they do not always work. Normally we limit ourselves to only a few rungs on the ladder, simply because the data becomes transformed so much that we may find it hard to describe what we did, even if the transformation is mathematically acceptable. Dealing with kurtosis can be tough. We use the same transformations we use for skewness, but they do not always work. If they do not work, there is no good test to tell us what to do. It becomes a judgment call about whether or not we should keep the variable. If we find an acceptable transformation, we can remove outliers one at a time until we get a distribution with no outliers. Outliers can be removed in the data view by right-clicking on the row of the observation we want to delete and using the cut command. This point is a controversial one, and we revisit it when we get into regression diagnostics. If any data is transformed or outliers removed, the dataset should be saved in a dataset with a different name using the Save As command. Always keep the original dataset without transformation and outliers unchanged in case you find a mistake and need to return to the beginning. Unlike the natural sciences, social research often relies on data that does not conform nicely to the normal distribution. This fact can undermine much of what we seek to accomplish with data analysis. We learned how to test a distribution for normality and what to do if the data is not normal. These statements are not our final ones on the topic. The question of dealing with normality and outliers returns at a more advanced level of analysis when we deal with regression diagnostics, where we review our work and perhaps change our minds.